Hi, today we're looking at Extrema. So these look at when we either have a maximum or a minimum value. Now, in some cases, we'll have multiples. So we'll look at some definitions to get started. So f of x has an absolute global maximum at x equals c if our function f of x is equal or less than f of c for all x values in our domain. F of x has an absolute global minimum at x equals c if f of x is equal or greater than f of c for all x values in our domain. Now we're going to look at relative local maximums or minimums. So f of x has a relative, which is a local maximum, at x equals c if f of x is equal or less than f of c for all x in an interval around c. So this one's not our entire domain, it's just in the area immediately around c. We also have f of x has a relative, which is also known as a local minimum at x equals c if f of x is equal or greater than f of c for all x in an interval around c. So once again, not our entire domain, just an area immediately around. So we have this graph. I'm just going to point out a few things on it. So we can see that essentially on this graph, on any graph, you're only going to have one absolute maximum and one absolute minimum. So our highest point here would be our absolute maximum. Now, down here, our lowest point is going to be an absolute minimum. Now, if we look at this graph, we also have relative minimums and relative maximums. So we have a relative minimum here because we can see as we're at this point, it's lower than any points immediately around it. Now, technically, this absolute minimum is also a relative minimum because we can see immediately around it, it is the lowest point. Now, if we look up here, we can see that this is a relative maximum because, once again, immediately around it, it is the highest point. Same as here would also be a relative maximum because immediately around it, it is the highest point. Now, what can be tricky is we can see down here we have our absolute minimum, which is also a relative minimum. This one up here is not a relative maximum. And the reason for that is because our line is essentially starting here. So although we have we know it's the highest point as we go to the right, we don't have any points as we go to the left. So because we're only looking at from one side, we can't say it is a relative maximum. Now this point here, as it just ends off, you know, it's a low point, once again, because it doesn't go back up, it just stops at that low point. It can't be called a relative minimum because once again, we can see it's the lowest point on this side, but it doesn't exist on the other side of it. And it's also not a absolute minimum because we can only have one of those and we have it over here. So with this, more info on these. I will just fill in a bit more information. So, like I was mentioning, our relative extrema, so maximum or minimum, do not occur at the endpoints of our graph, which can be thought of as those values in our interval. Bit more on increasing and decreasing functions. If we have a function f and we got f be a continuous function on a closed interval from a to b, and a is, or sorry, and a, between a comma b, but with the rounded brackets, it's differentiable, which means essentially it's smooth and continuous. Then if f prime of x is greater than 0 for every x on the interval, then our function is increasing on the interval a comma b. If it's less than 0 for every x on a comma b, then it is decreasing on the interval a comma b. Yeah, so for an example, we're going to find all intervals on which a given function is increasing or decreasing. And we have this function f of x equals x to the power 4 minus 8x squared. So first thing I'm going to do is take the derivative, because our derivative is going to give our slope at varying places. So, or I should say our derivative is the equation of our slope for this function. So our derivative of x to the power 4 is 4x cubed, and then minus the derivative of x squared is 2x multiplied by the negative 8, we get negative 16x. Now when I look at this, I can see I can factor a 4x out of both those terms. So it'll be 4x times x squared minus 4. Now what we'll notice here is this is a difference of squares. So we can factor that. So we've got f prime of x is equal to 4x times x minus 2 times x plus 2. Now we know from the previous set of notes we did, anywhere where where values of x for this make our f prime of x equal 0 are our critical points. So looking at this, we can see we have critical points at x is equal to 0, 2, and negative 2. So what I'll do next is just draw out a line graph. And on that line graph, I'll make sure I put some marks for each of those points and label them. So we have negative 2, 0, and 2. What we're going to do next is figure out whether our graph is increasing or decreasing on each of these intervals. So what we're going to do is take our equation for our slope and substitute in values for points that are between these critical points. So first I would look at, say, this section here. So I have to choose a point that's less than -2. So to make it easy, I'm just going to use -3. So we're going to do f prime of -3. So that's 4 times -3 times -3 minus 2 times -3 plus 2. Now that gives us -60. Now, because we have a negative value here, and we're only really concerned whether our value is positive or negative, I'm just going to mark this section where we calculate that with a negative sign on our line graph. Next, I'll choose a point between 0 and -2. We can choose any point between them, so we could have decimals, but I try to keep it simple, so I'm just going to use -1. So we've got f prime of -1 is equal to 4 times -1 minus 1 minus 2 times -1 plus 2, and that gives us 12. So once again, that's a positive value. It was between these two, so I'm going to say that I'm just going to mark this part of this line graph with a positive sign. Next, I'm going to look at this section. So a value between 0 and 2 would be +1. So I've got f prime of 1 is equal to 4 times 1 times 1 minus 2 times 1 plus 2. And that gives us -12. So because we got a negative value and it was between 0 and 2, I'm going to mark that with a negative. Now I'll do this section here. And I just have to choose something larger than 2, so I'll use 3. So I've got f prime of 3 is equal to 4 times 3 times 3 minus 2 times 3 plus 2, and that's giving me +60. So we've got plus. Now, the question had asked us to find all intervals on which the given function is increasing or decreasing. So essentially, these signs that we put in indicate increasing or decreasing. The positives are where it's increasing, the negatives are where it's decreasing. So we can say, therefore, f of x is decreasing on. So we're not going to include our critical points because we know at those points our slope is 0, so not increasing it, decreasing at those points. But we can see any point less than -2, so decreasing on when x is less than -2. And we can see it's decreasing between 0 and -2. So we can say 0 is less than x, which is less than -2. We can also say f of x is increasing on, and this would be where we had our positives, so between -2 and 0. So we'd have -2 is less than x, which is less than 0, and when x is greater than 2. This brings us to what's known as the first derivative test. The function f needs to be continuous with a critical point at x equals c. If f prime of x changes sign from positive to negative at x equals c, then f of x has a relative maximum at x equals c. So in other words, if we go from an increasing slope to a decreasing slope, we're going to have a relative maximum. If f prime of x changes sign from a negative to a positive at x equals c, then f of x has a relative minimum at x equals c. So in other words, if we are going from having a negative slope to a positive slope, we're going to have a relative minimum. Now, if prime of x does not change sign, then there is no maximum or minimum at x equals c. Okay, so we want to find our local maximum and minimum values of f of x equals x cubed minus 3x plus 1. So first thing we're going to do is take our derivative. So derivative of x cubed is 3x squared. Then the derivative of negative 3x is minus 3. We'll factor this, so this gives us f prime of x equals, we can factor 3 out, so that's 3 times x squared minus 1. We have a difference of squares here, so this is f prime of x equals 3 times x plus 1 times x minus 1. Now looking at this, we can find our critical points. And we can see we have a critical point at negative 1 and one at x equals positive 1. So just like the last example, I'm going to draw out a number line. Now in this case, we just have two critical points, so I'll just draw in two lines. So we've got one at negative 1 and one at positive 1. So I'm then going to calculate what my slope is to the left of this point, between these points, and to the right of this point. So to the left of this point, I might do f prime of negative 2. So that would be 3 times negative 2 squared minus 3, which gives us 9. So that's positive, so I will just put a positive here. Next, we'll do a point between negative 1 and positive 1. So I might do f prime of 0. So that would be 3 times 0 squared minus 3. So that's going to give us negative 3. So that's going to give us a negative value in that middle section. And then I'll do a point over here. So for example, f prime of 2. So that's 3 times 2 squared minus 3. And that gives us 9. Which is positive. Now from looking at this, here we had a positive slope followed by a negative slope. So we know that this should be essentially a maximum. Well, here we have a negative slope, so we're going downwards. And then we have a positive, so that means we then go upwards. So this one we know is a minimum. Now, the thing with this is it says find our local maximum and minimum values. So we also want to figure out what those exact values are. So I need to put those into our original function. So we know we had our maximum at negative 1. So that would be negative 1 cubed minus 3 times negative 1 plus 1. And that gives us 3. So we know we have a local maximum at negative 1 comma 3. We'll also figure out the exact value of its local minimum. So if we've got f of 1, that would be 1 cubed minus 3 times 1 plus 1, which is -1. So we have a local minimum at 1 comma -1. Okay, so next we're going to talk about the extreme value theorem. If f is continuous on a closed interval, a comma b, then f has both an absolute minimum and an absolute maximum value on that same interval. For example, find the absolute maximum and absolute minimum values of the function f of x equals x squared minus 4x plus 1 on 1 comma 4. So first thing I'm going to do is take the derivative of this. So that's going to give me 2x minus 4. So this one only has one critical point. And that's going to be at x equals 2. So my number line is just going to have a 1 point on it. And we're going to calculate our slope on either side of this. So if we look at this, we've got f prime of, let's say, 1 is equal to 2 times 1 minus 4. 2 times 1 is 2, minus 4 gives us -2. So we have a negative slope on this side. And if we do f prime of, let's say, 3, that would be 2 times 3 minus 4. So that would be positive 2. So that's positive on this side. So right now we can see that we have a negative slope and then going to a positive slope. So therefore we know that this is a minimum value. We don't know if it's an absolute or relative minimum. We'll do some more calculations to find that out. So what we want to do at this point, because we're on our absolute maximum and absolute minimum values on our function, we're going to calculate what our function is at both this point and the y values when we're at 1 as well as when we're at 4. So f of 1 would be 1 squared minus 4 times 1 plus 1, which gives us -2. Then we'll do f of 2, which is 2 squared minus 4 times 2 plus 1, which gives us -3. And then we have the end of our interval, which is 4. So that's going to be 4 squared minus 4 times 4 plus 1, which gives us 1. So we can see that this here was our largest y value. which means that we have an absolute maximum at 4 comma 1. Now we can see our lowest point was here, which was where we already knew we had a minimum. So we know that we have an absolute minimum at 2 comma negative 3.